Hi everybody, welcome to my video about Exam 2 review problems and solutions for calculus-based probability and statistics for scientists, engineers, and actuaries. The problems in this video are going to run the gamut from continuous random variables like normals, exponentials, chi-squared, normal approximations to binomials, to getting into multivariable distributions, bivariate random variables, their joint densities, their marginal densities, their conditional densities, curves of regression. We'll also do some descriptive statistics with some basic kinds of graphs like box plots and stem and leaf diagrams. And then we'll get into some theory about estimation, method of moments, and method of maximum likelihood estimators. So we'll start with a fairly simple problem. We're going to let x be a continuous random variable with a probability density function that equals c times x squared over a particular domain. The domain that I picked is x going between 1 and 4. It's understood that f of x equals 0 elsewhere. Part A is to find the value of c so that this is truly a PDF. It needs to integrate to 1. That's the key condition. Part B, find a formula for the CDF, capital F of x, the cumulative distribution function. It's going to be a particular antiderivative of the PDF. It's understood that it equals 0 when x is less than 1 and equals 1 when x is greater than 4. We're only interested in the formula between 1 and 4. Part C, find an actual particular probability that x is between 2 and 3. Part D, find the mean mu. And part E, find the variance sigma squared and the standard deviation sigma. Okay, so this is some basic practice with integrals. The very first thing we need to do is we need to make sure that f of x integrates to 1 over the relevant domain. So we need to integrate f of x from 1 to 4. And we need to set the result equal to 1 and solve for c. So this is a fairly easy thing to do. We integrate cx squared. We're going to get c over 3 times x to the third power evaluated from 1 to 4. That'll be c over 3 times 4 to the third, which is 64, minus 1 to the third, which is 1. This is a 63. 63 divided by 3 is 21. So this simplifies to 21c. We can set this equal to 1 and solve for c, and that means c is 1 over 21. Okay, so there's the answer to part A. On to part B. Find a formula for the CDF, capital F of x, a cumulative distribution function. It's an antiderivative of little f, but not any old antiderivative. Its value at the left endpoint of the domain here, where little f is positive, must be 0. So in particular, capital F of x can be written as the integral from 1 to x, not 0 to x, not negative infinity to x, but starting at 1, so its value when x equals 1 is 0, of little f of t dt, going ahead and using a dummy variable t. So we're integrating from 1 to x. The c was 1 over 21. We get 1 over 21 times, replace x with t squared. Now go ahead and do that integral. You get 1 over 63 t cubed evaluated from 1 to x. And that becomes 1 over 63 times x cubed minus 1 over 63 times 1 cubed, which is 1 over 63. You can leave the answer like this. You can also factor out the 1 over 63 like that. Either way, that's the answer for the CDF capital F of x. It's a particular antiderivative. Notice that when you plug in x equals 1, you get 0. And when you plug in x equals 4, you get 4 cubed is 64, minus 1 is 63, divided by 63 is 1, just like it should be. On to part C. We're going to find a particular probability. That probability that x is between 2 and 3 is the integral of the PDF from 2 to 3. But of course, by the fundamental theorem of calculus, that's a difference in values of the CDF. It's capital F of 3 minus capital F of 2. And if we want, we don't actually have to use the actual CDF. Maybe I should, just to emphasize it. That is the CDF. I'm saying we can use any antiderivative is what I was trying to hint at here. When I plug in 3, I get 3 cubed is 27, minus 1 is 26. I'll just go ahead and leave the 63, 1 over 63, factor it out. And then when I plug in 2, I get 2 cubed is 8, minus 1 is 7. Again, the 1 over 63 is really ultimately factored out of both of those terms. And 26 minus 7, that's going to be 19, so we get 19 over 63 for the answer. If I was after a decimal approximation, we see it's about 0.302. Okay, so that would be the probability that x is between 2 and 3. Part D, find the mean. Before we find the mean, let's make a guess as to approximately where it might be. There is the formula for the PDF between 1 and 4. Its graph is the graph of a quadratic between 1 and 4. It looks something like this. It's got a long left tail, but the majority of the mass, so to speak, is going to be near 4. We should expect the center of mass, which is going to be the mean, to be to the right of halfway between 1 and 4. Halfway between 1 and 4 is 2.5. We should expect something to the right of 2.5 for the mean. The mean is the expected value of x. By definition, that's the integral over the entire domain where f of x, little f of x is positive, 1 to 4, of x times the PDF, x times f of x. So we're going to integrate. Ultimately, c is 1 over 21. X times x squared is x cubed. That's the integral to do. That's going to give us the mean. Divide everything by 4, you're going to get 1 over 84, x to the 4th. When I raise that exponent by 1, evaluate from 1 to 4. It's going to give 1 over 84. 4 to the 4th is 256. 1 to the 4th is 1. Looks like we get 255 over 84. 255 over 84, if I've not made a mistake. Yes, and that is to the right of 2.5. It's about 3.04 when you round it. Okay? Hopefully I've not made a mistake. I'll put a note on here if there is a mistake. I do make mistakes, so I'm crossing my fingers hoping not to make a mistake. Part E, we need to find the variance and standard deviation, but before we can do that, we need to find the second moment. The second moment, expected value of x squared, is going to be the integral over the entire domain of x squared times the PDF. So you're going to integrate from 1 to 4, 1/21 times x to the 4th. X squared times another x squared up there, and don't forget your c. Divide everything by 5. 21 times 5 is 105, so I get 1 over 105, x to the 5th, evaluated from 1 to 4. 1 over 105, 4 to the 5th. That'll be 1,024, I think. 4 to the 5th is 1,024 minus 1, so this is 1,023 divided by 105. That's the second moment, not the variance yet, right? The second moment doesn't equal the variance. This is about 9.74. That's the second moment. The variance, sigma squared, or var x, is going to be the second moment minus the square of the first moment, minus the square of the mean. So that'll be 1,023 over 105 minus the mean was 255 over 84. We got to square that. All right, so here is the second moment. The first moment, again, is 255 over 84. Let me use parentheses here and just square it right away. 255 over 84, quantity squared. There's the second moment squared, or the first moment squared, excuse me. 9.74, 2857143 is the second moment minus the first moment squared. The variance is about 0.527. And then the standard deviation is going to be the square root of that. Standard deviation is the square root of the variance, and that is going to be approximately 0.726. Okay? So if I've not made any mistakes, that's number 1. Okay? So you got to be good at doing some basic integrals there. Let's move on to number 2. Let x denote the time in hours to locate and to correct a problem in software related to traffic lights. Assume x is normally distributed with a mean of 20 hours and a variance of 16 hours, which would mean, of course, the standard deviation would be square root of 16, 4. Sometimes these problems are given in terms of the variance, sometimes in terms of the standard deviation. Part A, find the probability that the next problem will require at least 24 hours to find it correct. Let's go ahead and start to do that. And part B is to find the hours at the fastest 10%, at the 10th percentile of x. It's going to be a small value of x because it's the fastest 10%. So we want to find the probability that x is between or greater than or equal to 24 here. And I made the numbers work out pretty nicely. We need to convert to a z-score by subtracting the mean of 20 and dividing by the standard deviation, not the variance. Square root of 16 is 4. So this turns out to be the probability that z is greater than or equal to 1, which, if you remember your 68, 95, 99.7 rule, should be approximately 32 divided by 2, 16% or so. With calculator, you can go to the distribution menu, excuse me, go to normal CDF. We could do it for the original distribution, which actually I already have in here. Upper value of 24, mean of 20, standard deviation of 4. This is going to be a CDF value, so the answer we want is 1 minus this. And yes, that is close to 16%. So this is about 0.159. You should feel comfortable using a table as well. This is a cumulative distribution function for a standard normal. If we go to z equals 1, 1.00, the CDF value is 0.8413. The answer is 1 minus that. 1 minus 0.8413, about 0.841, is 1.159. Okay? So that's the answer. You should be able to use technology or a table if I asked you to for my students. Probably didn't need quite so much room on this one. I needed more room on the top one there. Part B. How many hours do the fastest 10% of repairs take? Fast means x is small because x is the time to correct the problem. So we're after really the 10th percentile for x. Actually, I'm more used to doing this with the table. We're looking in the CDF table for an area equal to 0.1 as close as we can get. And it looks like that one right there is as close as we can get. And it corresponds to z equals negative 1.28 if we go up to the top there. Z equals negative 1.28 is at the 10th percentile. Notationally, sometimes this is written z sub 0.9, where the 0.9 actually refers to the area to the right of this being 0.9, 90%. It's a bit strange. This is the 10th percentile, but you put a 0.9 for the subscript there. And that means the x value at the 10th percentile, which I could put a 0.9 subscript there, would be mu plus sigma times z sub 0.9. So that's going to be mean is 20, standard deviation is 4. 20 plus 4 times negative 1.28. It's going to be less than 20. 4 times 1.28. And I need to subtract that, so I got 20 minus that. This is about 14.88 hours. That's how many hours or less do the fastest 10% of repairs take. Could you do it with technology? Could you find that? I haven't practiced this recently, so let's just try it. If you go to the distribution method menu, I think we need the inv norm there. We're looking for a CDF value where the area to the left is 0.1. And we can do it in terms of the original mean and standard deviation. Mean of 20, standard deviation of 4. 14.88, yes. Or it's rounding to 14.87, but yeah, this would be the more accurate one, actually, than the one we got from the table, because we're not at exactly 0.1 in the table. But good enough. Probably should round it to 14.9. All right, I didn't need as much room for that one. I should have given more room for the other one. The next problem is about a bivariate random variable with a joint density, discrete. It's given by a table, not a formula. It's a joint density, f sub capital X, capital Y. Now, I'm not multiplying capital X and capital Y when you see that. It's just notation. Discrete, bivariate, or two-dimensional random variable, x comma y, given by the table. And the way this is labeled is the x values are 1 and 2, and the y values are 1, 2, and 3. Part A says fill in the rest of the table to give the marginal density for x and the marginal density for y, and label which is which. When you add up across the rows, 0.3 plus 0.2 plus 0.1 is 0.6, and 0.2 plus 0.15 plus 0.05 is 0.4. Those are probabilities for these x values, 1 and 2. These numbers represent values of the marginal density, f sub capital X, of x, when you plug in little x equals 1 and 2. This is discrete, so this is giving us actual probabilities. No integration going on here. When I add up the columns, 0.5, 0.35, and 0.15, those are the values, probabilities values for y. Y can be 1, 2, or 3. This is the marginal density for y. Either way you add up here or here, it adds up to 1, as it should for the entire joint density. All the probabilities have to add up to 1. Okay, so those are marginal densities because they're in the margins of the table. That's why they're called marginal densities. B, find the probability that x equals 2 and y equals 1. This, by definition, is what the joint density value is when little x is 2 and little y is 1. F of 2 comma 1, that's in the table when x is 2 and y is 1. That's this right there. 0.2 is the answer. That's pretty easy. So it's a little trickier. I could think about it in a couple ways. I could think about x being 2 or y being 1, meaning I have to add up the probabilities in this row with the probabilities in this column, but don't double count. So it's really the same thing as this number, 0.4, the sum of the numbers in this row, plus 0.5. Don't double count this number, though. We need to subtract it off. 0.4 plus 0.5 plus minus 0.2 is going to be 0.7. This one was 0.2. Equivalently, we can think of this in terms of the general addition rule. We can think of this as the probability that x equals 2 plus the probability that y equals 1 minus the probability that x equals 2 and y equals 1. Really, the marginal density of x evaluated at 2 plus the marginal density of y evaluated at 1 minus the joint density evaluated at 2 comma 1, and it gives the exact same calculation here in the end. Okay, that's what we really did. Part D, assume you know that the expected value of x times y is 2.3, the expected value of x is 1.4. The goal is to find the expected value of y and then find what's called the covariance of x and y. The expected value of y can be written in terms of the joint density if you like, as a double sum, but it's easier once you've got the marginal density for y to write it in terms of the marginal density for y, to write it as the sum over all values of y. In this case, y goes from 1 to 3 of y times the PMF values. These densities are really probability mass functions instead of probability density functions, though my students know that our book calls them PDFs anyway in the discrete case. It's better to call them probability mass functions, PMFs. Probably better not to call it joint density, to call it a joint PMF. Anyway, coming back down here, this is going to be 1 times Fy of 1 is 0.5 plus 2 times Fy of 2 is 0.35 plus 3 times Fy of 3 is 0.15. So that's 0.5 plus 0.7 plus 0.45, and that will be 1.65. There is the expected value of y. It had to be between 1 and 3. What's the covariance? Use the shortcut formula for the covariance, not its definition. The shortcut formula says it's the expected value of x times y minus the product of the expected value of x and the expected value of y. I'm given the expected value of x times y is 2.3. Expected value of x is 1.4, and the expected value of y we've just figured out is 1.65. Unlike variances, covariances can be negative. Is this one or not? It's hard to tell at first here. 1.4 times 1.65 is 2.31. We got 2.3 minus 2.31. It is negative. It's negative 0.01 and oh, so close to 0. It's like, oh boy. That's pretty strange maybe that it's so close to 0. That doesn't typically happen. I say here in E that x and y are not independent. Give one reason why not. And a good enough reason is that the covariance is non-zero. Even though it's really close to 0, it's still technically not equal to 0, and it's not a rounding error or something. So because of that, that's enough to say that the x and y are not independent, because the covariance of x and y is non-zero. There's a theorem that says when x and y are independent, the covariance is 0. The contrapositive of that means, therefore, if the covariance is not 0, then x and y are not independent. Unfortunately, just because the covariance is 0 doesn't mean x and y are independent. It's not an if and only if. X and y being independent does mean the covariance is 0, but just because the covariance is 0 does not mean x and y are independent. It's unfortunate that it does not. It would be nice if it did imply that. Part F, find the values of the conditional density f sub, what's this thing? That's a conditional random variable. Shorthand notation for the random variable y when we are given that the random variable x equals the value little x, where little x in this case is 2. What's the conditional random variable for y when capital X equals the value of 2? It's a conditional density, really a PMF, probability mass function, for that variable that involves y. We want to evaluate this for y equals 1, 2, and 3. What do you need? Well, you need the formula for it. The formula is, in general, for this thing, it's the ratio of the joint density divided by, we're assuming capital X takes on a value of little x. So we need to divide by the marginal density for capital X evaluated at little x. So if I do this when little x is 2, I'll just write a 2 there, and little y is 1, I get the joint density value when little x is 2 and little y is 1, divided by the marginal value when little x is 2. Hopefully I don't make a mistake. Easy to make mistakes. The joint density values come from the original values in the table. When x is 2 and y is 1, there's got a 0.2 there. And the marginal density, f sub x, evaluated at 2, is going to be this value, 0.4. And in each one of these cases, we're going to end up dividing by that same quantity, 0.4. So this is 1/2, 0.5. For the next one, the numerator is different, but the denominator is the same. Still going to divide by 0.4. The numerator, f, the joint density evaluated at 2, is the 0.15, right there. So this is 0.15 divided by 0.4, and what's that going to be? 3/8, I guess. 0.375. And then the final one will be 1 minus the sum of these two. It should be 0.125, but let's check it. Oops, this is a 2 here. Joint density evaluated at x is 2, y is 3, divided by the same number as before, the marginal density evaluated at 2. Joint density value is 0.05. 0.05 divided by 0.4, yes, is 1/8, is 0.125. Yes, and these things do have to add up to 1 as they do. Sorry, I couldn't quite see it there. All right. Next page. Now we deal with a continuous bivariate random variable. Instead of doing summations, we're going to do integrals, though I made them relatively easy. Continuous bivariate random variable. This truly is a density now. It's defined over a rectangle. Okay, it's assumed to be 0 elsewhere. This rectangle in the xy plane looks about like this. There's 2, here's 1. That's the rectangle domain where the PDF joint density is positive, assumed to be 0 elsewhere. I do teach my students about non-rectangular domains, and theoretically you should be able to do it, but certainly dealing with a rectangular domain is easier. And I made this problem easier than I could have, partially to help with my grading, to make things go smoother. The formula for the marginal density is this. Use the fundamental theorem of calculus to confirm what the answer should be for that marginal density. So I'm telling them what the answer should be, so I'm only looking for the correct work here. So we need to integrate this joint density, 3/8 times x plus y squared. With respect to y, we're integrating out the y, treating the x as a constant. That's the trickiest part about this. Treat the x as a constant. Bring the 3/8 out front. Integrate x with respect to y. You're going to get xy. And treating x like a constant. Integrating y squared with respect to y gives you 1/3 y cubed. Y goes from 0 to 1. The answer does depend on x. We want a marginal density for x. Plug in first y equals 1, and you'll get x plus 1/3. Right? When y is 1, that's an x, that's a 1/3. Minus what I get when I plug in y equals 0, which is 0 plus 0. Simplify, distribute the 3/8 through, you get 3/8 x. 3/8 times 1/3 will be 1/8. Yes, we have verified this formula. And yes, it is understood to be correct when x is between 0 and 2. Part B, note that the joint density is non-negative and is assumed to be 0 elsewhere. This is over the rectangle here. Show work to verify that the double integral of it equals 1. You can already use the work you've done in Part A. We've already done the inner integral here of this double integral. Now we need to do the outer one. So we really need to integrate the marginal density that we just found with respect to x. That means integrating 3/8 x plus 1/8 with respect to x. That's going to give 3/16 x squared plus 1/8 x. X goes from 0 to 2. We'll get 0 when we plug in 0. What do we get when we plug in 2? We get 3/16 times 2 squared is 4 plus 1/8 times 2. Let's do a little cancellation here. Looks like we got 3/4 plus 1/4 equals 1. Yes, we have done it. We are happy, happy, happy. Okay, it does integrate to 1. Part C, the conditional density for y given capital X equals little x is this. This is a continuous conditional density. It truly is a density. Its formula is the same as in the discrete case, but you don't interpret it as a probability in the continuous case. You can interpret it as a density value. It simplifies to this. You can double check these calculations. To get from here to here, finally, you would multiply the top and the bottom by 8. When you look at this formula, you want to think of x as fixed and y as the variable. Okay, that's the way to think about that formula. But evidently, no matter what x is, this evidently is a density. That's kind of amazing. That's surprising when y is between 0 and 1, no matter what x is. But x does have to be between 0 and 2. Based on this fact, write down in simplified form, but do not evaluate an integral that will give the curve of regression of y and x. Mu sub y given x of x. And then in part D, we're going to try to interpret a value of this thing. What does this mean? Yeah, what does this mean? No pun intended. What does this mean? It is a mean for this conditional random variable, y given x, which is just shorthand really for y given capital X equals little x. What's the distribution of y when x is known to be little x? When capital X is known to be little x? Random variable is a y value, but its mean does depend on x. And so ultimately, this is a function of x. Wow, kind of confusing. But it is a mean of a y, so it really is an integral with respect to y. of, it's a mean, so it's an expected value of y, you got to integrate not just this function, but y times that function. With respect to y, as y goes from 0 to 1, I did say simplified. I mean, go ahead and plug in the formula for little f and go ahead and distribute the y through. In simplified form, distribute the y through the numerator. Here you'll get a numerator of 3xy plus 3y cubed. And the bottom is going to stay the same, 3x plus 1. You're integrating this with respect to y. Ultimately, the answer does depend on x. And we can think of this mean as a function of x, and we could graph it if we like. Actually, doing this integral is not that hard. You'd split this fraction up into two pieces and just treat everything involving x as a constant. And it turns out, you could check it, that would be a good exercise, that the formula for mu simplifies to this. Okay, and the goal in part D is just to calculate this value and briefly describe what it represents, understand what it represents. So to calculate that, we just plug the number in. Plug in x equals 1.5, we'll get 3 plus 6 times 1.5, looking at this formula right there, divided by 4 plus 12 times 1.5. So that will be 3 plus 9 over 4 plus 18 is 12 over 22. Which is 6/11ths, which is what, 0.5 something repeating? I forget. 6 divided by 11, 0.54 repeating. But more importantly, what does that represent? It represents the mean value of y when x is known to be 1.5. And it's got to be between 0 and 1, because y is between 0 and 1, always, no matter what x is. Yeah, and it is amazing that that's a PDF no matter what x is when y goes between 0 and 1. If you integrate this from y going from 0 to 1, you will get 1 no matter what x is. That's pretty amazing. And here's the mean that we just found. Well, we just wrote the formula for it. Here's its formula. This is the formula involving an integral. This is the simplified formula. This is what it evaluates to when x is 1.5. So yes, this is the mean of y when x is known to be 1.5. Mean of y when x equals 1.5. To be more precise, it's the mean of the conditional random variable y given x when x is 1.5. Pretty fancy stuff here. Is it related to, is the curve regression related to actual linear regression? Yes and no. I mean, that curve that we got is nonlinear. We'll get there by the end of the semester. Number 5, a baseball player has a 300 career average, getting hit on 30% of official at-bats. Assuming the player has 100 official at-bats in the first month of the present season, use a normal approximation to the probability that he will have between 28 and 35 hits inclusive during that first month. Show your work or explain. If x is the number of hits in 100 at-bats, I know with my students we've talked about this kind of example before. You're counting the number of successes in a certain number of trials, whether you have a fixed probability of success on each trial. X is binomial with parameters n equals 100 and p equals 0.3. Okay, this means x is, or x has a binomial distribution with n equal to 100 and p equal to 0.3. And that means its mean, its expected value, is n times p. That's a special formula for binomials. 100 times 0.3, which is 30. You could expect to get 30 hits in 100 official at-bats. And the standard deviation turns out to be, for a binomial, square root of n times p times q, where q is 1 minus p. These are special formulas for binomials. They don't work in general. This is square root of 100 times 0.3 times 0.7. 30 times 0.7 is what? 21. 30 times 0.7, yeah, that'll be 21. Square root of 21 is about 4.582577. I'll use a fair number of decimal places and only round at the end. It's probably overkill, but oh well. We're trying to use a normal approximation. X is not normal, it's binomial. However, it can be approximated by a normal distribution, normal random variable, approximating a discrete random variable with a continuous one, with the same mean and same standard deviation. However, traditionally in our book we write the variance here. So that's going to be mu, and this is going to be sigma squared, technically for the binomial, but then I'm going to use this normal random variable to approximate the binomial. We're trying to find the probability that x is between 28 and 35 inclusive, so I need less than or equal to's here. That's going to be approximately the probability that y is between the same numbers, or though more ideally, to get a better approximation, use the half-unit correction. This probability could be thought of as the sum of some areas of some rectangles centered at first 28, then 29, etc., up through one centered at 35, and therefore they don't all have the same height. Therefore, we want to ultimately integrate the PDF, the normal distribution here, between 27.5 and 35.5. That's called the half-unit correction for continuity. If the between 28 and 35 was exclusive, not including 28 and 35, I'd have strict inequalities here and here, and you would not include the bars above 28 and 35 for the area, so you'd go from 28.5 to 34.5 here. And we can convert these to z-scores. 27.5 minus the mean, which is 30, divided by the standard deviation, square root of 21. The y becomes a z. Do the same thing for the 35.5. What do these numbers become? Negative 2.5 divided by square root of 21, which is already in the calculator there. This becomes approximately negative 0.55. And this one, 5.5 divided by square root of 21. Approximates to about 1.2. There should have been a less than or equal to here. And ultimately, for the standard normal distribution, whose CDF is commonly called capital phi, you get capital phi of 1.20 minus capital phi of negative 0.55 for the answer. And I'll just do that in my calculator. That's just notation for the CDF of a standard normal distribution. We could have called it capital F. Normal CDF, and we can do a lower and upper here that are both finite numbers and not, off to minus infinity, so to speak. Well, okay, I guess okay. Let's just get an answer. So let's just go to negative 0.5 here, 0.55 here, 1.2 there. We are using a standard normal here. Roughly 0.59 in the end is the answer. Okay, roughly 0.59. Bunch of approximations going on here. There's one. Really, here's another with these things, and more approximations with the calculator. Roughly 0.59 if I have not made a mistake. Number 6, fairly quick problem about chi-squared random variable. Chi-squared random variable, 7 degrees of freedom. Find a, 1 minus a CDF value. And since it's continuous, I can put a strict less than or a less than or equal to there. And I'm just going to use a table for this one. It is on the calculator. Well, maybe I should do it both ways. For a table with 7 degrees of freedom, my table looks like this. 7 degrees of freedom. The 14.1 I did pick special to be on the table. 7 degrees of freedom, it's below 0.95. The CDF value's up there. This is approximately 1 minus 0.95. The answer is approximately 0.05. And that would mean also in the 7 degrees of freedom case that little chi-squared sub 0.05 is approximately 14.1. And that is the kind of thing I'm asking here. What's little chi-squared 0.25, where the subscript represents an area to the right. It's 1 minus a CDF value. It's not a CDF value itself. I'm noticing I'm running out of battery here. My thing must not be plugged in. All right. That's better. Still 7 degrees of freedom. The 0.25 is an area to the right. Therefore, the area to the left, the CDF value is 0.75. With 7 degrees of freedom, that's 9.04. That's a CDF value, an area to the left, shaded to the left. The subscript represents a 1 minus CDF value. Again, 9.04 is what we're after there. Sorry about that. It's weird that chi-squared, you put the subscript to be the degrees of freedom there, but not there. This number does not represent the degrees of freedom. You need to know what the degrees of freedom is. 7 is problem. And on to number 7. Theoretical kind of problem. Let x1 through xn be a random sample from a distribution that's geometric random variable with parameter p. Geometric is a discrete random variable that counts the number of trials until the first success, where p is the probability of success on each trial. Its mean, its expected value, is 1 over p. If you've got for example, a 10% chance of something happening. Well, okay, let's say you're rolling a die and you're trying to get a 1. You got a 1 in 6 probability of getting a 1 on any given roll. Therefore, the mean number of rolls until the first success is going to be 1 over 1/6, which is 6. Okay, that's geometric. It's discrete. The goal is to use the method of moments to find what's called an estimator, p hat for p. Share your steps, however briefly, but do not have to give reasons for your steps. Okay, what's the method of moments? It's going to be based on this fact right here. The expected value of x, its mean, is 1 over p. What you do is you replace that with its first moment, with what's called the first moment. It is a first moment. Replace it with a symbol for an estimator of the first moment. This is a mean. M1 could be thought of as a theoretical estimator for mu, a statistic that we can get from a random sample that is a good estimator for mu. Usually we don't call it M1, usually we call it X bar, capital X bar. The sample mean, take all these random variables that have the same distribution, add them together and divide by n, is what's called an unbiased estimator for the population mean mu. Population meaning the actual theoretical distribution. Replace that with X bar, an estimator for the first moment, sometimes called M1. Replace P with, well, we call it P hat. That's a statistic that's going to be an estimator for P. The goal is to solve this equation for P hat. It's very easy. Cross multiply, so to speak, or multiply both sides by P hat and divide both sides by X bar. P hat is going to be 1 over X bar. That's the answer. Okay? There's not much to do. This method of moments can become more complicated in more complicated situations. For example, with gamma distributions, where you've got 2 parameters, an alpha and a beta, and you're trying to find an alpha hat and a beta hat, and you replace formulas for the expected value of x with an M1, and the expected value of x squared, the second moment, with an M2, and you try to solve the resulting system of equations for alpha hat and beta hat in terms of M1 and M2. If you've never done this before, that sounds really confusing. Okay, my students, you've done this before if you've gotten to chapter 7 in the book, with some examples that are in the book and also problems that you've thought about. Do that replacement, solve for the estimator. This is a theoretical estimator or statistic obtained by the method of moments. We just have 2 more pages here. Oh, this looks like a long problem. Well, it's not as long as it seems. Well, we got to plug these numbers into your calculator, though I've done that already ahead of time. thinking ahead here. Go to your stat mode and edit, and list one is all these numbers. What is this about? This is ozone levels around Los Angeles. That's related to smog. Have been measured as high as 220 parts per billion. Can cause eyes to burn and are a hazard to plant and animal life. These data were obtained about the ozone level near Seattle, April 1990, in parts per billion. Those seem kind of high. I mean, they're not too far from 220. Part A, construct a double stem and leaf diagram for these data. 2 rows for each stem. Do these data appear to be skewed, and if so, what direction, left or right? Left skewed or right skewed? With an ordinary stem and leaf diagram, you'd put, in this context, stems to be 16, 17, 18, and 19, the first 2 digits of these numbers. But with a double, you want to do each of those twice. Though, yeah, with the 19, I guess we'll need to do it twice as well. Then you put a line. These are the stems in this diagram. Now we want to do the leaves. And the way you do it with a double one is when your last digit is 0, 1, 2, 3, or 4, put it with the first occurrence of the stem. And when it's 5, 6, 7, 8, or 9, put it with the second occurrence. So we see 2 160s, so put 2 zeros, then a 161, another 161, 3 162s, 3 163s, 1 164, stop there. For the 165, go to the next stem. Make sure you line these digits up vertically because you're trying to really make a sideways graph, a histogram, so to speak. Line these things up vertically. Put the 5 under the first 0, put the 7 there under the second 0, put the 7 there under the 1, the first 1, 8 under the second 1, 9 under the first 2. Then we go on to the next line. 170 gets a 0 there, and 172, 173, then 176, 178, 179, 180, 185, and 196. Technically, we should put the 6 down there. These are the leaves. The point of this is a graph, really. You need to turn it sideways to see it. Effectively showing you the distribution of the data. A histogram, in a sense. That's not bars, but these digits. And this tells you it's got a long right tail. It's right skewed. Okay? This is definitely right skewed. Yes, the data do appear skewed, very skewed, right skewed because of a long right tail. If we had one where the tail was off to the left, it would be left skewed. Boxplot means we need to find the 5-number summary first. The min is certainly easy, min and max. Min is the smallest number, which is 160. The max, I like making min all lowercase and max all uppercase, is the biggest number. That's 196. What's the median? Often called M. Well, how many numbers are there? There's 9 numbers in each row. 9 times 2 is 18, plus another 7 is 25. N is 25 here. The median location is at position n plus 1 over 2. That'll be 26 over 2 is 13. If you go 13 from either the lowest one or the highest one, you'll get to the median. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I could have just said jump down to here. 10, 11, 12, 13. It looks like that's the median. Let's double check by going backwards from the top. 7 there, 8, 9, 10, 11, 12, 13. Yes, the median is 167. For the quartiles, there are different ways of doing it depending on which book you're reading. Q1 and Q3, and I like making the first quartile a lowercase q and a third quartile a uppercase q just for fun. What I recommend to my students doing, it seems simplest to me, is to go back to the data, and when the median is in an odd spot, as it is here, the 13th spot, if it's an exact number in the data, so to speak, break up the data, the smaller part of the data and the larger part of the data, into 2 groups, each of size 12 in this case. So in those subsets of the original data set, n is 12, and 12 plus 1 over 2 is 13 over 2 is 6.5, and so the first quartile, I need to go average the 6th and the 7th spots. 1, 2, 3, 4, 5, 6, and 7. They're both 162. So first quartile is going to be their average, which is still 162. Now do it for the bottom, the higher numbers, 1, 2, 3, 4, 5, 6, 7. The average of these two is going to be the third quartile, and the average of 173 and 176 is 174.5. The calculator does happen to give the same answer there. If I go to Stat, Menu, and Calculate, scroll down, min 160, first quartile 162, median 167, third quartile 174.5, that was the most suspicious one, and max of 196. A box plot takes these numbers and makes a box plot, also called a box and whisker plot. It's important to make sure you mark numbers with the scale in such a way that they are appropriate distances apart. So if that's 10 units right there, then I want the same distance to be 10 units from 170 to 180, approximately like this. Of course, you can't make it perfect, but get it decent. And you make lines at these 5-number summaries. There's the min at 160 right there, the first quartile 162 right about here, median 167 right about here, third quartile 174.5, really close to the middle there, right about there, and maximum was 196 right about here. Oops, maybe a little bit further to the right. And then you draw a line through the middle of all these, and you sort of highlight the mid part between the first and third quartiles to emphasize that, you know, that's a solid set of data, so to speak, because sometimes outliers, well, you could call 196 here possibly an outlier, greatly affect the picture. So this is kind of like less important parts of the picture. And this emphasizes it's right skewed. Now, if 196 were not in there, effectively, well, 185 would be the maximum. It would be right here. It would still be right skewed. Okay, it's right skewed. The third quartile and the maximum are further from the median than the first quartile and the minimum are. Use these data to give unbiased estimates for the mean and variance of the ozone level. You may use your calculator without work, but write down appropriate symbols. Okay, X bar is an unbiased estimator for the mean ozone level. That can be written as the expected value of X bar is mu. Therefore, an unbiased estimate of the mean is the value of little x bar, the mean of the sample, which is the sum of all the numbers divided by 25 in this case, how many there are. But it is in the calculator output, except I erased it. Stat, calculate. 169.04 is the observed value of X bar based on this random sample. Parts per billion if you want units here. That would be an unbiased estimate for the mean. Mu, we would say mu is approximately this. This is a theoretical idea, emphasizing that X bar as a statistic formed from a random sample by adding the random variables and dividing by n is unbiased. It's a random variable whose expected value is mu. This is an observed value of X bar based on the sample, the random sample that we happen to have. It's also true that S squared is an unbiased estimator for sigma squared, the population variance. That does not mean S, the sample standard deviation, is an unbiased estimator for sigma, the population standard deviation. Unfortunately, it's not. So we want now an observed value of S squared. So on the calculator output, it's important to do the S, not the sigma. Use S. That's the main point, is use S, this 9.02995, and square it. 9.02995 squared will be our observed value of S squared. 9.02995 squared. About 81.5. That is an unbiased estimate for the population variance based on the fact that capital S squared is an unbiased estimator. These are theoretical. This is practical. Part D, assume the data follow an exponential distribution with parameter beta. I'm telling you the maximum likelihood estimator for beta can be shown to be beta hat equals x bar, the sample mean. Find a maximum likelihood estimate for beta. Hint, there's not much work to do here. You just got to know something. And the thing you got to know is that for an exponential random variable, beta is its mean. And therefore, a maximum likelihood estimate for beta, the mean, is the sample mean. Therefore, beta hat equals x bar that we get from the maximum likelihood method, which we will do on the next page, is an unbiased, is a maximum likelihood estimate for beta. So we need what you're told in this problem. You also need to know that the mean of an exponential random variable with parameter beta is beta itself. Some books call it lambda instead of beta. Some books call it k instead of beta. Some books just cut to the chase and call it mu right away, actually. But our book, for my students, uses the letter beta. Now, one more page. Very first problem on this page is about maximum likelihood estimators. Probably the toughest problem on the exam here. And the last problem is about actuarial science application using some special notation, including an A bar for something called the net single premium. If you don't know about actuarial science and don't care, you can skip that one, but I'm teaching it to my students here. Yeah, this number 9 is probably the toughest one. It's most theoretical. Let little x1 through little xn be a random sample of observed values, so they're little x's instead of capital X's. Capital X's would be random sample in terms of random variables. From the distribution of x, an exponential random variable again, with parameter beta. Find the value of beta that is most likely to produce these numbers. Big hint, part D of the last problem tells you the answer. It's going to be x bar. But how do you do that? How do you derive that with this method of maximum likelihood? You create something called the likelihood function. It's going to be a function of the unknown parameter, in this case beta. By definition, it's the product as I goes from 1 to n. So this is a capital pi here. It's not the number pi. It means product. Product, instead of summation, of values of the PDF. In the discrete case, the PDF would really be the PMF, the probability mass function. These would be actual probabilities that you're multiplying, giving an overall probability of observing the given random sample based on what beta is. In the continuous case, they're not really probabilities. They're probability densities. But you still use the same method. You still multiply these things. You need the formula for the PDF of an exponential here with parameter beta, where beta is the mean. The formula you really should memorize is 1 over beta times e to the negative x over beta. Though instead of writing an x here, I write an xi because I've got an xi here. This is representing the ith number in this observed random sample. Doesn't look so simple. We can simplify it a little bit. You got n factors of 1 over beta. That's the same as 1 over beta to the n. And when you're multiplying a bunch of exponentials, you can really add their exponents. For example, e to the negative x1 over beta times e to the negative x2 over beta, for example, can be written as, well, add those exponents and bring the negative sign out, negative x1 plus x2 over beta, property of exponents. Do the same thing here in the general case, and you're going to get e to the negative summation I goes from 1 to n of the xi's all over beta. What do we want to do with this function? We want to maximize it. That's why this is called maximum likelihood estimators. As a function of beta. You're kidding. No, I'm not kidding. But this is often the case. It's easier to maximize its natural log. The log likelihood function of beta is the natural log of the likelihood function of beta. So L of beta is the likelihood function for this situation. LL of beta is the log likelihood function. Maximizing the log likelihood function also maximizes the likelihood function. The value of beta that makes this as big as possible also makes this as big as possible. And this turns out to be easier to deal with. You need to take the ln of all that, and that's actually easier than it sounds, or easier than it looks, using properties of logarithms. It's the ln of 1 over beta to the n plus the ln of e to the negative sum of the xi's over beta. And that simplifies quite a bit. This is the same as beta to the negative n. And so you can bring the negative n out in front. You can write this as, by property of logarithms, negative n natural log of beta. Yeah, negative n natural log of beta. And then here the ln and the e are inverse functions, so they cancel each other out, and you're left with minus 1 over beta times the sum, I goes from 1 to n, of the xi's. We want to maximize this thing, so we better find its derivative with respect to beta. Differentiate this thing with respect to beta. Derivative of natural log of beta is 1 over beta, so I get negative n over beta. 1 over beta is the same as beta to the negative 1. When I differentiate beta to the negative 1, I get a negative 1 beta to the negative 2. The two minus signs will cancel, and you get a 1 over beta squared. And the sum of the xi's is just a constant. It just stays there. It doesn't depend on beta. I want to find the critical point of this. I want to set this equal to 0 and solve for beta. And when I do so, that'll be my maximum likelihood estimator. And it should be x bar. Rearrange. Well, we can multiply everything by beta and write this as negative n plus 1 over beta times the sum. I goes from 1 to n. It is assumed here that beta is non-zero. You do have a positive mean. That equals 0. Rearrange again. 1 over beta times the sum of the xi's equals n. Divide both sides by n and multiply both sides by beta. And that means beta is the sum of the xi's divided by n. And those are lowercase xi's, so this is a lowercase mean. X bar, it is a mean of observed data. This is data. But it does mean, well, so this is the most likely value of beta to produce these data, so to speak. It does mean then that the maximum likelihood estimator, as a theoretical estimator, typically written as beta hat, is going to be capital X bar. Okay? Once again, this is essentially data-based. This is more theoretical. But yeah, that is the hardest problem on the test probably here. Could we do this by differentiating the likelihood function itself? Maybe, but I think I don't want to try it. And certainly not for this video. Last problem. Let t be a survival type random variable with survival function sigma. Sometimes sigma is called s. Unfortunate here, sigma is not a standard deviation, and s is not a standard deviation. It's just notation for survival functions, which are complements of CDFs. It's equal to 1 for t, negative t, and e to the negative 0.0 t for t greater than or equal to 0. This is modeling the lifetime of something, and it's probably not a good model for a person. It might be for a light bulb, perhaps, depending on what the units for t are. Part A says to find this probability that you survive at least 10 units of time. That's just going to be a value of the survival function. That's what the survival function represents. Sigma of t is 1 minus the CDF, and that will then be the probability that capital T is greater than little t. It's continuous, so you could use a greater than or equal to as well here. So this is just sigma of 10. Look at the formula for sigma. This is going to be e to the negative 0.2. E to the negative 0.2, about 0.819. Oh, 4 decimal places, 0.8187. Part B, find the force of mortality, mu of t. Mu is not a mean. So unfortunate with this notation here. There is going to be a mean in part C, but force of mortality is not a mean. My students know it's defined to be the relative rate of decay of the survival function. It's a relative rate of decay because we use a negative sign and a derivative. It's a relative rate of decay because we also divide by the survival function itself. This does end up being a positive quantity, though, because two negatives make a net positive. Sigma prime here is going to be, with the chain rule, negative 0.02 e to the negative 0.02 t. And sigma itself is e to the negative 0.02 t. Those divide out. The two negative signs cancel. We get a constant function. This is true for all positive t. The force of mortality is constant. Essentially, you can interpret the force of mortality as in this way. If you assume you make it to a certain age, like t equals 10 or something, what's your probability of dying in the next small amount of time, delta t? You'd multiply 0.02 times delta t. How small does delta t need to be to make that inaccurate? It depends on the situation. If you're imagining making it to at least 10 years and you're wondering what's your probability of dying in the next day, if you assume you make it to 10 years, you'd multiply this by 1 over 365. So it'd be effectively 1 over 50 times 1 over 365, which would be pretty small, as you would hope. Find the mean, mu, of t. Oh, and this is based on something called the Darth Vader rule. And I have no idea why it's called the Darth Vader rule. So the mean of t is the expected value of t, which by definition is the integral over all t, this case 0 to infinity, of t times the PDF of t. That's the PDF of t, which is going to be negative the derivative of the survival function, it turns out, which is a positive thing. It's positive 0.02 e to the negative 0.02 t. But to do that integral, we'd have to use integration by parts. By the Darth Vader rule, this only works for survival random variables, survival type that only take on non-negative values. Darth Vader rule, you'll get the same thing if you integrate the survival function. And you don't have to have a t in front of that. So you don't have to use integration by parts. We're just going to do this integral right here. And this is an exponential distribution, so the mean is actually beta, and the beta is going to be 50 in this case. This is going to give us 50 in the end here. I'll have negative 1 over 0.02 e to the negative 0.02 t, evaluated from 0 to infinity. Technically speaking, I should put a limit sign in here. It's an improper integral. That's the same as negative 50. When I quote-unquote plug in infinity, I get 0. When I plug in 0 into e, I get 1. Okay? Now, I'm not literally plugging in infinity. I'm imagining letting t go to infinity for the first term there. So we get negative 50, mistake somewhere. I guess I'm already taking care of the negative sign out there. So, okay. So we get negative 50 times negative 1 is positive 50. Beta in this case is 50. 1 over beta is 0.02. Okay. Last part of the last problem, part D. If the interest rate is 0.08, 8% per year, say, find A bar, the net single premium, NSP. This is an actuarial science concept. It's a mean, it's an expected value. Of what, though? We need to describe the meaning of A bar as well. A bar, by definition, is the expected value of something called Z bar, And this z has nothing to do with standard normal. What is z bar? It is sometimes written v to the capital T power. Also sometimes written e to the negative delta times capital T power, where v is called the annual, say, discount factor. It's 1 over 1 plus the interest rate, 1 over 1.08 in this case. And delta is the natural log of 1 plus I, natural log of 1.08, and that'll be approximately 0.076961. 0.076961. Delta is called the force of interest. You could also call it a continuous interest rate if you liked. The expected value of that based on the given survival function and its negative derivative, which is the PDF. So we're going to need to integrate over all t, e to the negative delta t times the PDF, which is negative sigma prime of t. The PDF is really this thing right there. 0.02 e to the negative 0.02 t. Delta is approximately this. So this simplifies to approximately 0.02 integral from 0 to infinity. Add the exponents, you'll get e to the negative delta plus 0.02. Hope I have not made a mistake here. So a negative 0.096961 t dt. I think this is right. I think I haven't made a mistake. I'll put a note if I have. So again, the e to the negative delta t comes from right there. The 0.02 e to the negative 0.02 t, that's the same as 1 over beta e to the negative x over t over beta, where beta is the mean. It turns out to be 50. 1 over 50 is 0.02. So what do we get here? We get approximately negative 1 over, or negative 0.02 over 0.096961 e to the negative 0.096961 t, evaluated from 0 to infinity, but it's really a limit. In the end, we're going to get the positive version of this number here, just like we got the positive version of that number up there, 50. 0.02 divided by 0.096961. It's about 0.206, or say about 21 cents. Because what is this all about? I didn't really describe this before. If an insurance company pays an actual amount of $1 at the time of death, a benefit, what is this representing? If you know about the time value of money, v to the t represents the present value of a $1 benefit paid t years in the future. It's less than 1. It's worth less now. We're trying to find the expected value of that over many t's, so to speak, over many, many people who buy this insurance policy. That's what it represents. It represents the average expected value of a $1 payment at time of death for all your clients, for your insurance company. So if this is an accurate model of people's lifetimes, which I'm sure it's not, if it were, you'd want to charge them at least 21 cents for a $1 benefit, or say $2,100 for a $10,000 benefit. Okay, now that seems like a lot to charge them. So that's probably related to the fact that this is not an accurate model, and this is kind of a high interest rate as well. So it's not accurate, but that's what it would represent. It would be the mean expected value of the present value of all of the future payments of $1 at time of death. Okay? Thanks for watching. Have a good day.